Okay, hi everybody, we're back with another past paper walkthrough. This time it's the Higher Physics 2022 Paper 1 multiple choice questions. There are 25 questions and it's a 45-minute paper. As usual, we suggest that you have a look at the questions first, try them yourself and then come back when you're ready and follow through the walkthrough. Page 2 always contains the data sheet. That's some of the numbers that we might need as we work our way through the question. So first section then is our dynamic universe, usually the first 10 questions or so. Let's jump straight in with question 1. A ball is thrown vertically upwards and falls back to its starting position, and the acceleration time graph represents the motion of the ball. Now notice it has a constant negative acceleration, and we are asked which of the following velocity time graphs represents the same motion. So the quick way to do this is to look for a velocity time graph that has a constant negative gradient. And if we check all the other ones, we can see that A is the only one that has a constant negative gradient. And that's the kind of maths way to do it. Although the physics way of doing it is just think about what's actually happening. The ball is thrown vertically upwards and then falls back to its starting position. So if we think about what's actually happening, then the ball is going to decelerate upwards, so it's got a negative acceleration in the positive direction. So we're taking upwards as positive, and that's why the ball starts off with an initial positive velocity, and that velocity is going to decrease as it slows down and reaches its maximum height and then accelerates in the opposite direction. So answer A is correct. Question 2. A student uses the apparatus shown to determine the acceleration of a trolley as it moves down a ramp, and the trolley is released from rest at point P and moves down the ramp. So it's going to have an initial velocity at the top of the slope, u equals 0. Now let's see what we're asked here. The time taken for the car to pass through the light gate is displayed on an electronic timer, and the vehicle's acceleration A is determined using the relationship v squared is u squared plus 2as. And the student makes the following statements about the terms u, s and v. U is equal to 0. Yes, it is at the top of the slope. S is the length of the card. No, it's not. S is the length of the ramp that it rolls down. And V would be the speed at the bottom of the ramp. So is that the distance between P and Q? No, it's not. The V in this relationship is the instantaneous final velocity at the bottom of the slope. That's as it passes through the light gate. So to work out what that V would be, it would be the length of the card divided by the time it takes to pass through the light gate. So only statement 1 is correct. That's A, 1 only. Moving on, question 3. A spacecraft unloads cargo on the surface of the moon. The gravitational field strength on the moon is 1.6 newtons per kilogram. And a package of 3 kilograms moves down the ramp. The component of the weight of the package acting parallel to the ramp is, well, whenever you see that statement, then you would use this relationship, which isn't on your relationship sheet, but we recommend you just remember it, the force on the slope relationship, F equals mg sine theta, and let's sub in all the values. 3 is the mass, g is the gravitational field strength on the moon as 1.6, and the angle was 34 degrees, so sine 34. And if you do all that on your calculator, you will get 2.7 newtons, and that corresponds to answer B. Question 4. 2 blocks are suspended from a ceiling by ropes as shown, and which row in the table shows the tension in the rope at point X and the tension in the rope at point Y? Well, the thing to remember here is that the tension in X is supporting the total weight. That's the weight of both masses that's below it. The total mass will be 12 plus 15 is 27 kilograms. So that weight is 260 newtons. And the tension at Y is only supporting the 15 kilogram mass. and that's got a weight of 150 newtons to 2 sig figs. So let's check what row is correct. We want 260 and then 150. That's answer E. Question 5. During an experiment, a student inside a lift stands on a Newton balance, and the mass of the student is 50 kilograms, and the lift accelerates upwards at 1.2 meters per second squared. So we have a mass and we have an acceleration. The obvious thing to do here then is to use F equals ma and work out the unbalanced force that's acting. So let's do that. F equals ma. 50 times 1.2 is 60 newtons. Now notice that is one of the answers, but wait a minute, that's the unbalanced force that's causing the acceleration. We're asked for the reading on the Newton balance, so don't forget about the weight of the guy that's standing on the scales. His weight will be his mass times gravity on Earth. 50 times 9.8 gives us 490 newtons. So that would be his weight when he was at rest, and so therefore we have to add on the unbalanced force that's producing the acceleration, and we'll get a total reading that's on the Newton balance of 550 newtons. That's answer D. Moving on then, question 6. Water flows at a rate of 1 times 10 to the 6th kilograms per second over the Victoria Falls. And Victoria Falls are 120 metres high. This looks like a gravitational potential energy question. What are we asked? Let's see, the total power delivered by the water in falling through 120 metres is... We've got answers that are in watts. So let's work out the potential energy of that mass of water at that height. So it's 1 times 10 to the 6th times 9.8 times 120 gives us a potential energy of 1.176 times 10 to the 9 joules. Now that's the mass of water that is falling per second over the Victoria Falls. So if we work out the power, which is the energy produced per second, is 1.2 times 10 to the 9 divided by 1, which is 1.2 times 10 to the 9 watts. That's answer B. 6B. Question 7. A spacecraft passes the Earth at a speed of 0.4 c, and a light on the spacecraft pulses on and off. A passenger in the spacecraft measures the time between the pulses as 2.5 seconds. So an observer on the Earth will measure the time between the pulses as... Well, this is a time dilation and special relativity question. And don't forget, with these questions, all you're usually asked to do is plug numbers into the time dilation relationship. So just go straight to your relationship sheet, make sure you copy it down correctly in your rough working, and substitute the numbers in. So it's T dash that we're looking for. So the T on the right hand side there is the time as measured on the spacecraft. That's 2.5 divided by the square root of 1 minus 0.4 c over c all squared. Now the trick here is to cancel out the c's, and you're left with the square root of 1 minus 0.4 squared on the bottom. And if you do all that on your calculator, you'll get an answer of 2.7 seconds. That corresponds to answer C, 7C. So an observer on the Earth will see the light flashing at a slower rate. Okay, moving on, question 8. A student makes the following statements about the expanding universe, and we have to choose which of these statements is or are correct. Number 1. The evidence supporting the existence of dark matter comes from estimations of the mass of galaxies. Well, that's correct, because from our observations of the light coming from distant galaxies, then there doesn't appear to be enough matter in the galaxies to hold them together. And this supports the idea that there must be some additional matter present that we can't detect that's providing the gravity to hold the galaxies together, and that's dark matter. Statement 2. The evidence supporting the existence of dark energy comes from the accelerating rate of expansion of the universe. Well, yes, that's true as well. We can now detect that the rate of expansion of the universe is increasing, and we don't know what's causing that, so scientists have given that the name of dark energy. And statement 3, the peak wavelength of radiation emitted by hotter stars is longer than that for cooler stars. Well, no, that's not true, because hotter stars are more blue. That means they have a shorter wavelength, not a longer peak wavelength. So statement 3 is incorrect. So 1 and 2 are correct. That's 1 and 2 only. That's answer D, 8D. Question 9. This is about the Doppler effect with sound. A police car is travelling at a constant speed of 31 metres per second towards a stationary observer, and the siren on the car emits a sound with a frequency of 820 Hz. Speed of sound in air is 340 metres per second, so the frequency of sound heard by the observer is... Well, let's go straight to our relationship sheet and find the relationship for the Doppler effect for the observed frequency of a sound from a moving source. And there it is. Now remember, this relationship can be quite tricky because there's 2 F's and 2 V's. Actually, there's 3 V's in it. The V on its own is the speed of sound, and the V with the subscript S is the speed of the moving source. Now this source is moving towards a stationary observer, and if it's approaching you, you use the minus sign on the bottom there. So the observed frequency will be the actual frequency, which is 820 Hz, times the speed of sound in air, which is 340, over the speed of sound in air minus the speed of the moving object that's moving towards the observer. And if you do all that on your calculator, it gives you an answer of 902 Hz. That corresponds to answer E, 9E. So that's all the questions from the Our Dynamic Universe unit. So now we're moving on to particles and waves, starting at question 10. A proton enters a region of magnetic field as shown, and we are asked the direction of the force exerted by the magnetic field on the proton as it enters the field is. Well, we're going to need a right-hand rule here. Remember, your first finger shows you the direction of the magnetic field, so that's going to be pointing from left to right. The direction that the charge is moving in, or the current if you like, is down the page, and your thumb should show you the direction of the magnetic force. Now, the right hand rule is for a negative charge. So if you do your right hand rule here, your thumb is going to be pointing into the page. That would be for a negative charge. This is a proton, which is a positive charge, so it's the opposite of that, so it's out of the page. Question 11. The masses of 3 particles are shown. We've got an electron, a proton and a Higgs boson. And we have to say how many orders of magnitude greater is the mass of the Higgs boson compared to the mass of a proton. So we're only looking at the powers of 10 here. The Higgs boson is 2 powers of 10 larger than the proton. So that's answer B, 11B. Question 12. A proton consists of 2 up quarks and a down quark, and a student makes the following statements about protons. So, statement 1, protons are baryons? Yes, they are, because baryons are made of 3 quarks. Statement 2, protons are hadrons? Yes, they are, because the hadrons are made of quarks. And protons are fermions? Yes, they are, because the fermions are the matter particles. So all 3 are correct. That's 12E. Question 13. Following statement represents part of a radioactive decay series. Nucleus X undergoes alpha emission to produce nucleus Y. The nucleus Y undergoes beta emission, and we have to identify nucleus X. So let's draw it out again and see if we can work this backwards. So we've ended up with bismuth with an atomic number of 83 and a mass number of 214. So the nucleus that has emitted a beta particle must still have a mass number of 214 but an atomic number of 82. Because when a beta particle is emitted, the mass number stays the same, but the atomic number goes up by 1. So now if we know what nucleus Y was, we can trace back to nucleus X, because if X emits an alpha particle, which is the same as a helium nucleus, then its mass number must have gone down by 4, and its atomic number has gone down by 2. So we're looking for 218 on the top, 84 on the bottom. So the only answer it can be is answer C. And we don't even have to look up the periodic table here, because there's no other options for 21884. So it can only be polonium 21884. It's answer C. Okay, question 14. It's another nuclear reaction here. It is plutonium that is decaying to uranium with the emission of an alpha particle. And we're told what the mass is before the reaction and the mass after the reaction, and some of the mass is lost during the reaction. And we have to find the energy released. So it's E equals mc squared, where m is the lost mass. That's 1.1 times 10 to the minus 29. And you'll find that number by subtracting the mass afterwards from the mass before. And then we multiply that by 3 times 10 to the 8 squared. And you get an answer of 9.9 times 10 to the minus 13 joules. That's answer D. Question 15. The irradiance of light incident on a surface from a point source is 20 watts per square metre, and the distance between the point source and the surface is 5 metres. If the point source is now moved to a distance of 25 metres from the surface, then what is the new irradiance of the light incident on the surface? Well, straight to your relationship sheet here. I1d1 squared equals I2d2 squared, where I1 is your initial irradiance, that was 20 watts per square metre, and d1 is your initial distance, that was 5 metres, and don't forget to square that distance, and that will be equal to our new irradiance I2 times the new distance, which was 25 metres. Don't forget to square it, and then rearrange for I2, so I2 will be 20 times 5 squared over 25 squared. And if you do that on your calculator, you get an answer of 0.8 watts per square metre. And that corresponds to answer B. Now, alternatively, if you would rather do it by ratios, if the distance is 5 times greater, then the irradiance will be 5 squared times smaller. That's 25 times smaller. So 20 over 25 means your new irradiance is 0.8 watts per square metre. Question 16. This is interference. Light from a laser is incident on a grating as shown, and we see a series of interference maxima on a screen, and a student makes the following statements about the interference pattern. Statement 1. Increasing the distance between the grating and the screen increases the distance between the observed maxima. Well, yes it will. This is like moving a projector back. The image on the screen is going to be bigger or more spread out. Statement 2. Increasing the distance between the laser and the grating increases the distance between the observed maxima. Well, no it won't. That'll have no effect whatsoever. And statement 3, decreasing the distance between the slits on the grating decreases the distance between the observed maxima. Well, let's have a wee look at the relationship m lambda equals d sine theta. If the wavelength of the light stays the same, but we decrease the distance between the slits, then sine theta must increase, so the distance between the maxima must increase. So statement 3 is incorrect. So the only one that is correct is statement 1, one only. That's answer A. Question 17. Which row in the table shows what happens to the speed, frequency and wavelength of red light as it passes from diamond into air? So it's going from more dense to less dense. So the speed is going to increase. Frequency always stays the same. and the wavelength will also increase. Okay, on to question 18 then, and these are the electricity questions. The output from a signal generator is connected to an oscilloscope, and the trace seen on the oscilloscope screen is shown. The Y gain setting on the oscilloscope is 2 volts per division, that's vertically, and the time-based setting is 5 milliseconds per division horizontally. Now, the peak of the wave on the screen is 3 divisions vertically, so it's 2 volts per division vertically, so 3 times 2 is 6 volts peak. And we are asked to give the RMS voltage. Well, that's the peak divided by root 2. 6 over root 2 is 4.2 volts. So let's have a look in the table. So it's either A or B for the RMS voltage. And we need to find the frequency as well. So we can work out the period of the wave. That's the time for one wave from the horizontal setting on the oscilloscope. So one wave is 5 divisions, and the time-based setting is 5 milliseconds per division. So 5 times 5 is 25 milliseconds. So the period of the wave is 25 milliseconds. So the frequency will be 1 over the period. That's 1 over 25 times 10 to the minus 3 is 40 Hertz. So looking at our answer table again, RMS voltage was 4.2 volts, the frequency 40 Hertz. So our answer is B. Question 19. 3 resistors are connected to a 3 volt power supply as shown. The power supply's got negligible internal resistance, and we have to work out the power dissipated in this circuit. So we need the total resistance of the circuit first. Now these 2 resistors then are in parallel. The 2 6 ohms in parallel gives us a total of 3 ohms, and that 3 gets added to the 9 ohm resistor because they're in series with each other. So the total resistance of the circuit is 12 ohms. Now to work out the power, we know the supply voltage and the total resistance of the circuit. So we're going to use V squared over R. That'll be 3 squared over 12 is 9 over 12, which is 0.75 watts. That's answer C. Question 20. Still on series and parallel circuits. We are asked to show which row in the table shows the total circuit resistance and the potential difference across X and Y. So let's simplify the parallel bit of the circuit first. We can add the 2 5s in the top, the 2 5s in the bottom. That gives us 10 ohms in parallel with 10 ohms. And if you remember, you're adding resistors in parallel from last year. Then 10 in parallel with 10 gives us a total of 5 ohms. So if the parallel section's got a total resistance of 5 ohms, then the total resistance of the whole circuit will be 15 ohms. That's the 5 plus 5 plus 5. So total circuit resistance means our only possible answers are A or B. And then we want the potential difference across X, Y. And remember, between X and Y, we've got a total resistance of 5 ohms. So let's draw a simplified version of the circuit. And we want the voltage across that middle section. Well, they're all 5 ohms, so they will share the 12 volt supply equally. So the voltage across X and Y is 4 volts. So that's answer B. Moving on, question 21. Circuit is set up as shown, and the resistance of the variable resistor is set to 6 ohms. What's the lost volts due to the internal resistance of the battery? Well, the total resistance of the circuit is 10 ohms, so we can work out the current from the battery just by using Ohm's law, I equals V over R. So V is our supply voltage, that's 12 volts, and R is the total resistance of the circuit, that's 10 ohms, so the current will be 1.2 amps, and then we can use that current to find the lost volts due to the internal resistance. So the lost volts will be the current times the internal resistance, 1.2 times the 4 ohm internal resistor. That's 4.8 volts. That's answer B. 22. Circuit is set up as shown. The battery again has negligible internal resistance, capacitor is uncharged, and the switch is now closed. When the reading on the voltmeter is 7 volts, what will be the charge stored on the capacitor? Well, let's put a voltmeter across that capacitor. So when the voltage across the resistor is 7, the voltage across the capacitor must be 5 volts because they add up to the supply voltage. And then to work out the charge stored on the capacitor, we go to our relationship sheet and we find the relationship Q equals CV. We know that the capacitance of the capacitor is 220 microfarads. That's 220 times 10 to the minus 6 times the 5 volts. That gives us an answer of 1.1 times 10 to the minus 3 coulombs. That corresponds to answer C. That's quite tricky. A lot of people would have used the 7 volts there and of course got one of the other answers. Question 23, again a circuit is set up as shown and the capacitor is initially uncharged, then the switch is closed. Which graphs show how the voltage across the resistor, the voltage across the capacitor and the current in the circuit vary with time as the capacitor charges? So we're looking for a graph of VR, VC and the current on the ammeter. So it's probably easiest to start with the voltmeter across the capacitor, because as the capacitor charges, the voltage across it will increase. And if that voltage is increasing, then the voltage across the resistor will decrease. And since the supply voltage is constant, if the voltage across the resistor decreases, then the current must decrease. So we are looking for graphs here. VR decreases, VC increases, and the current decreases. So decreases, increases, decreases. Then the only possible answer is E. Question 24. It's about semiconductors. Which row in the table describes the conduction band and the gap between the conduction band and the valence band in an insulator? Well, it might be easier to talk about the band gap first. In an insulator, the band gap is very large. So if we have a large gap between the conduction band and the valence band, the only possible answers are going to be C or E. Then let's think about the conduction band. Well, in an insulator, the conduction band is unfilled. That's 24C. And the last question, question 25, is an unknown relationship, an unfamiliar relationship. And in this type of question, all you have to do is pop the numbers into the relationship and we have to work out the mass of the Triangulum galaxy. So what are we told? A star orbits at a radius of 4 times 10 to the 20. The orbital speed is 120 kilometers per second, and we have to work out the mass of the galaxy. So m equals v squared r over g. We know that v is 120 kilometers per second, so don't forget to convert kilometers into meters. It has to be in meters per second, and don't forget to square it. The radius was 4 times 10 to the 20. And big G from your data sheet is 6.67 times 10 to the minus 11. And if you do all of that on your calculator, you'll get an answer of 8.6 times 10 to the 40 kilograms. That's answer E. This is also a good example of that if you didn't change the 120 kilometers per second into meters per second, then you would have got answer C. Or if you substituted in the 120,000 correctly but forgot to square it, then you would have got answer D. So all the right, wrong answers are there. Make sure you double check your calculations. That's it. That's the end of the multiple choice section. 25 questions. We've done it in just about half an hour. You've got 45 minutes to do it. Make sure you do as much rough working as you need to do. There's plenty of space for that at the back of the booklet. That doesn't get marked. That'll just get thrown in the bin. But take your time and lay things out nice and neatly, and that'll hopefully lead you to the right answer. That's it. Hope that helps some of you. We'll see you in the next one.